Hello everyone, and welcome to the Rotational Inertia Post-Practicum. In this practicum, you were supposed to experimentally determine the mass of a disk, and then the mass of an annular cylinder, and you had to rotate them around an axis other than one through the center of mass. Now, of course, you needed to remember that we could figure out the experimental rotational inertia by using the apparatus that you should be very familiar with. In which case you needed to use this equation to calculate the rotational inertia of that object about an axis not through the center of mass, because I didn't want to make it too easy for you. Of course, if you don't know where this equation came from, you should be able to derive it really from basic principles, but it is in pretty much all of the pre-labs that we've done most recently. Remember, though, that in this case, the R is the radius of the large pulley that you're wrapping the string around. That's from the torque, right? That's the distance from the axis of rotation to the point of application of the force, which for the large pulley is about 0.024 meters. The M is not the mass of the disk or the annular cylinder, it's the hanging mass off the side. Again, it's part of the torque, right, equals I alpha thing, equation that we used to get here. And these two things are alpha, that's not A's, that is the angular acceleration, which you could get by taking the slope of the angular velocity versus time graph. And hopefully this is not anything that was too shocking, because if you didn't remember this, you were kind of out of luck. But notice here that none of this has to do with the radii and the masses of the disk and the annular cylinder. Right? That came in afterwards. Okay, but at least in terms of figuring out the experimental rotational inertia, you were essentially doing torque equals I alpha and solving for I. You were applying Newton's second law for rotation, right? And this was the equation we got out when we found all the pieces and parts. Now, once you had this value, then for the disk, right, we know that the rotational inertia of a disk about a central axis is 1/2 mr squared. We derived that in class. You're just supposed to know that. Right? It's one of the ones you're just supposed to know. And you even should be able to derive it from basic principles. Okay? That's something that's in the AP curriculum. But I did not want you to actually work around the center axis. I wanted you to choose one of the other axes, right? Just to make the life a little harder. So say if you screw it in here instead of the center of mass. Okay? Then you need to use the parallel axis theorem. I suppose you could do the calculus again and change your limits of integration, but that would be way harder. The parallel axis theorem says take the rotational inertia about the center of mass, which is that, and add it to mh squared, where m is the total mass of the disk, and h is the distance from the center of mass to the new axis of rotation. If you chose the outer edge point, then that means h, which is this, is really r. Now, I suppose you could have chosen that other point, but then you would have had to figure out what h was in that case. So I'm just going to solve it for this, right? It's the same math, basically. If you picked a different point, you just have a different h. So if we plug in an r there, we get 1/2 mr squared plus mr squared, which is, of course, 3/2 mr squared. Look at how quick that is. Right, to be able to figure out the rotational inertia about that point. And then, since we have the rotational inertia experimentally, we could solve for the mass. Right? Now you got to measure the radius, right? Plug in your rotational inertia, and you should have gotten, I hope, a value that was within the ballpark for the mass of the disk. The annular cylinder was similar, but a little more complex, because the formula is a little more complex. We derived in the pre-practicum an expression for the rotational inertia of an annular cylinder about a central axis of 1/2 m times the quantity r2 squared plus r1 squared, where r2 squared was the radius to the outer edge and r1 squared was the radius to the inner edge. So if we again use the parallel axis theorem and plug that center of mass rotational inertia in, right, we get this. The question here is, what is h? Well, really it depends where you went here. I believe you had the ability to screw in the, or to attach, if you will, the annular cylinder about a point on the inner edge, and you could also apply it to a point on the outer edge. The difference is going to be what h is here, right? So I'm going to do this as if you put your axis of rotation on the inner edge of the annular cylinder, in which case h is really just R1, right? That would be from the center of mass to the new axis, right, is what h is. So that would be R1. Now again, if you chose the outside, you would just plug in an R2 there, right? But the math's going to be basically the same. So we plug that in, and now we go on our merry algebra way to figure this out. If we distribute through the 1/2 and the total mass, right, we get that. We can combine the like terms, the 1/2 mr1 squared plus the mr1 squared. I also did a couple of steps of algebra, right? That would be 3/2 mr1 squared, but I don't like having fractions, so I multiplied both sides by 2, and I got this, right? 2 times the rotational inertia is mr2 squared plus 3 mr1 squared. Again, that's 1/2 plus 1 is 3/2. Move the 2's. And then if we factor out a mass, leaving us with mass times r2 squared plus 3r1 squared, and then divide, right? There's our total mass equation. With me there? Now, a little more algebra, perhaps, than the disk, but that's because the rotational inertia is more complex, because it's a more complex object. But again, not very long, and certainly shorter than the calculus way of doing this. So you could plug in your experimental rotational inertia, right, about whichever point you chose, and then just plug in everything here. Now again, this is assuming that you used an axis of rotation at R1. If it was R2, basically the 3 would just move, right, because the math would be the same otherwise. So you'd have 3r2 squared plus r1 squared if you did the other way. But either way, you hopefully got a good result for your experimental mass.